Alright, so in the last field theory video, we proved that the symmetric group of degree n is non-solvable for this type of n. So let us now come back to our main field theory discussion with this lemma. So what this lemma says is that there is a field f which contains all the nth roots of unity for some particular positive integer m, and we have chosen an element a in f which is non-zero. Let k be the splitting field of this polynomial x to the power n minus a, and obviously this is a polynomial over f, and the splitting field also is over f, it's an extension of f. Then two claims are there. The first claim says that if we adjoin any root of this polynomial u to f, then the resulting extension is nothing but k, the splitting field. And the second claim is that the Galois group of this polynomial over f is abelian. So let's now see the proof. Now in the beginning of the proof, we have to properly interpret what it means for this field to contain all the nth roots of unity. In general, an element in a field is said to be an nth root of unity where n is some positive integer if the nth power of that element is 1. Now if you go back to that section which is named more about roots, you may remember that in that section at one stage we made an assumption that for the rest of this chapter we are only going to consider fields of characteristic 0. So keeping that in mind, actually these nth roots are complex numbers. Okay, the complex nth roots of unity, of which there are n elements, n such numbers are there, and we know very well what those numbers are. So that's how we are going to start the proof. Since f contains all the nth roots of unity, it in particular contains this nth root of unity, which we are going to denote by this Greek letter xi, e to the power 2 pi I divided by n. You know what this complex number is. This is what it is, and we know that it also has a name. It's called the primitive nth root of unity, and it has a property. Being an nth root of unity, of course, its nth power is 1, but the thing is that no smaller positive power is 1. In other words, we know this. We know that xi to the power n is 1, but xi to the power m, for some reason I am unable to, I can write it on paper, but on board I cannot seem to manage it, is not equal to 1 for all integers m that are positive and less than n. Alright. Now we want to prove this. So let us start by taking one such root. Let u be, oh by the way, where will u lie? U will obviously lie in K. Why? Because K is the splitting field of this polynomial, so by definition K has all the roots of the polynomial. And in fact, with that, it is also the smallest extension of F with that property that it has all the roots. Smallest in terms of what? In terms of degree. So let U belonging to K be any root of this polynomial. Then the author says that, yeah, here I have been able to write psi. These are also all roots of our polynomial. Oh, what am I writing? Minus a. The question is how? Let us just see briefly how. You just take any element, any complex number from here. Well, can we say it's a complex number? Okay, it's just some field element in K, right? After all these elements are going to be elements in K, because U is coming from K and these of course are in F, and so all these things are in K. So let us take any element from here, say this, where I satisfies these inequalities. There is in fact no need to consider the case where I is 0, since in that case you just have U, and U by definition, I mean by choice, is a root of x to the power n minus a. And now we calculate the nth power of this. The nth power is going to be, using all the rules of exponents, everything, alright, this is 1, right? And what is u to the power n? Since u is a root of x to the power n minus a, substituting for x here, that is writing u in place of x, you are going to get 0. That means u to the power n is a. That's how you have a. That means this indeed satisfies the polynomial this. This minus a is equal to 0. That's why we are saying that all of these are also roots of this polynomial. Now the next thing we are going to observe about them is that they are all distinct. We claim that how many numbers do you see in this list? N, right? Starting from this one up to this one, there are n minus 1 of them and this extra u. That all these n elements are distinct. Contrary to this claim, suppose they are not distinct. Suppose some xi to the power iu is equal to xi to the power ju for different I and j. For some I and j like this. Okay. Then first you can cancel u from both sides to get this, and so psi to the power j minus I should be equal to 1. But there is a question that arises here. How do you know that u is not equal to 0? To answer that question, you can proceed like this. You see, what do you know about u? What is u? U is some root of x to the power n minus a, right? That means u to the power n minus a should be equal to 0. It is equal to 0. Now, if u is equal to 0, then a would be equal to 0. But this is a contradiction, because our choice of a is that it's a non-zero element from F. That's why u is not 0. And that's why we can cancel u from both sides. And after that, again, a similar thing, similar problem arises here also. From this equation, writing this equation means what actually? It means dividing both sides by xi to the power I. Is xi itself non-zero? Yes, it is also non-zero. Why? Because xi is this complex number, right? And this is a complex number whose absolute value is 1. It lies somewhere on the unit circle centered at the complex number 0, on the complex plane. So obviously it's non-zero. That's why this is justified. However, this itself is now going to create a problem because of this thing. So let me just keep this much for now. But, okay, let us now look at these inequalities. Because I is less than j, subtracting I from j gives us a positive integer. But at the same time, since I is non-negative, so subtracting I from j likely reduces j. That's why it is less than or equal to j. And I say likely because it may not actually reduce j precisely when I is 0. In that case, j minus I is simply j. In other cases, it is strictly less than j. And j is less than or equal to n minus 1, and n minus 1 is less than n. And what does this say? This says that for an exponent m that is a positive integer and less than n, this power cannot be equal to 1. Here, however, we are just getting just that. But this is not possible because it's contradicting that condition. So, our supposition is wrong. i.e., the roots are all distinct. Now you may remember a general field theory result which says that if you have a polynomial whose degree is n, then in any extension field there are at most n roots of that polynomial. And here for our polynomial x to the power n minus a, we have already found n roots. So that means there is no more, and these n roots are all distinct. So that's it. That's all the roots that this polynomial has. Now since psi belongs to F, we have all these roots lying in the extension obtained by adjoining U to F. How? Well, U of course belongs to this extension, and all these powers of xi not multiplied by U, okay, only the powers of xi, all of them belong to F because xi itself belongs to F, and that is why these products all belong to Fu. This means what? This means that over the field Fu, you can split the polynomial x to the power n minus a completely as a product of linear factors. What are those linear factors? Those linear factors are these. In fact, you can factorize x to the power n minus a, or you can split this polynomial completely as a product of linear factors like this, because these scalars are all belonging to Fu. So this factorization is happening over Fu, or in the ring this. And the usual way of expressing this is to write like that. So Fu completely splits this. All right. That alone, however, doesn't make Fu the splitting field of our polynomial, because maybe a smaller extension of F also is able to split this polynomial, but it cannot. Why? Because of this next thing. Now, note that if some extension, I will give it a name so that we can see. I mean, without just simply writing one sentence, let's just elaborate a little bit. Now note that some extension, what shall I call it? Let me call it L. L of F that doesn't contain U cannot split the polynomial completely. Why? That's because in order to split a polynomial completely, the extension must contain all the roots of this polynomial, and one of those roots is u. If this doesn't contain u, then of course you cannot write x to the power n minus a as a product of those linear factors in the ring Lx, in the polynomial ring Lx, if L doesn't contain u. So, any extension of f that has to split our polynomial must contain u. There is no other choice. Now, any such extension which has all the roots of x to the power n minus a, saying this and saying that any extension of f which splits this polynomial are basically the same thing, actually the same thing. So, for any such extension, say not this L but over some extension L prime of f that splits the polynomial, it has to contain u as well. Alright? For any such extension L prime, this should be true because we know that this is the smallest extension which contains f as a subfield and u as an element. Right? However, we know that such a subfield already is K, and that is why Fu has to be nothing else but K. So, any such extension must have Fu, let us also write as a subfield, although we know even if you don't write as a subfield, it's known in what sense that extension contains Fu, but there is no harm in stressing this. Okay. Hence, K is equal to Fu. Do you get this? Do you get how this is coming? If still this is not clear, you can further elaborate it like this. You know that by definition the splitting field is the smallest extension of f which contains all the roots of this polynomial. What further have we proved? We proved that Fu contains all the roots of this polynomial, which is an extension of f. Now, we have also concluded that any extension of f that contains all the roots of our polynomial must contain Fu. In particular, K must contain Fu, but at the same time Fu must also contain K due to the minimal nature of K, and that's why these two are equal. So, we have proved half of the result. Now, next we have to prove that the Galois group of our polynomial is abelian. So, for that, let us take any two elements in the Galois group. Let sigma and tau be two elements elements in the Galois group. Remember that this is the Galois group of our polynomial. Why? Because K is the splitting field of this polynomial over F. That's why. Okay. Now our aim is to show this, that sigma tau is equal to tau sigma. We already know something else. Oh, and by the way, what are sigma and tau? These are automorphisms of K, which fix every element of F, both of them. So from that fact that they fix F entirely, you can at least say something right now. Let me just say it in the beginning itself. Since sigma and tau both fix every element of the underlying field F, we have alpha, say alpha is an element of F, sigma tau equal to alpha, sigma fixes alpha, so alpha sigma is simply alpha, and similarly alpha tau is alpha, and this is also equal to alpha sigma. I can again write alpha as alpha sigma, and then again this alpha can be written as alpha tau. So what we are trying to say here is that at least on the elements of F sigma tau and tau sigma have the same effect, namely they have no effect. Actually they do not do anything, they fix the elements of F. Alright. Now next we are going to see what happens to U. What does sigma tau and what do sigma tau and tau sigma do to U? Okay. And here we are going to use the fact that since U is a root of the polynomial x to the power n minus a, so the images of U under both sigma and tau are also roots. How? Let's just see that. Although we have seen this before when we discussed roots of polynomials, let's once again see how. You see, U is a root of our polynomial. This means we have this, right? Now if say we apply sigma to both sides of this equation, equal to 0 sigma. Sigma is a field homomorphism, an automorphism actually, so it respects addition, multiplication, everything, equal to 0. Because it's a homomorphism, so it maps 0 onto 0. Further, because it is coming from this group, so it fixes every element in F. In particular, it fixes A. So A sigma will be A again. So we see that just like U is a root of this polynomial, so is U sigma. Okay, so we are going to use this fact. Now, since U sigma and U tau are both roots of our polynomial, we know all the roots. U sigma is equal to xi to the power I u and u tau is equal to xi to the power j u for some I and j. Okay. We know what the conditions on I and j are, but that's not a very big deal. There is no need to write those things again. Okay. Now we can calculate u sigma tau and u tau sigma. U sigma, let me do the calculation in the middle like this. That way it will look nice. U sigma tau, first of all, is the tau image of U sigma. Now what is U sigma? This. And now tau respects multiplication because it's an automorphism. So it will distribute itself in this product completely, and the next step would be this. Oh, okay, there is no need to take I outside, in fact. U tau. Because xi belongs to f, so any power of xi is after all an element of f, and tau fixes every element of f, so this is going to stay like this. U tau, however, is this. So we get this. Similarly, this calculation is also similar, so I am not going to do it in detail. Tau sigma, if you apply that on u, you are going to get j plus I u. If you keep all the orders and everything in your calculation intact, if you do not change that, you are going to get j plus I. But these two are equal. U sigma tau is equal to u tau sigma. Now since k is equal to fu and every element of fu it consists of a combination of elements of f and u, right? And sigma tau and tau sigma have the same effect on u as well as on every element of f. So we have alpha sigma tau is equal to alpha tau sigma for all alpha belonging to k equal to fu. Hence, as functions sigma tau and tau sigma are equal, this implies that the Galois group is abelian. Okay, and that completes the proof. Now after this proof there is an observation, and the observation is this. We have realized k as fu right? And this is the splitting field of our polynomial over f. So by a previous result, we know that K is a normal extension of f by theorem 565. K is a normal extension of f. Well, you have to keep that in mind, that the condition, the hypothesis on f should be there, that f contains all the nth roots of unity. You should not forget that. And do you remember the definition of normal extension? An extension K of f is called normal if the fixed field of this group is nothing but f itself. And throughout the rest of this chapter, this section actually, not chapter, we are going to assume that f contains all the nth roots of unity for every positive integer n, not just for some particular n, but for every n, f contains all the nth roots of unity, all the nth roots of unity. This is the assumption that we are going to have for the rest of this section. The next result that comes, we are not going to prove this one today, however, but still let's see what the result says. Now we are going to say something decisive. This is taking us towards the final thing of this section. So this result is, its statement is quite straightforward. With this assumption in mind, let Px be a polynomial in fx and let it be solvable by radical over f, of course. Then the Galois group of Px over f is solvable, is a solvable group. And it's this thing that because of which we call such groups solvable groups. So we are going to prove this result in the next field theory video, and I am just going to stop here itself. So that's just all for tonight. So see you tomorrow. What do we have? Oh, tomorrow, class 11 thing. There is no video. There are only some problems that I will post in the community section. But anyway, if you want, you can check the community section. So see you tomorrow with that itself. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.